In this video, I wanted to summarize the main points of phasor analysis. So, what is phasor analysis? Well, we want to express these sinusoidal waveforms. These could be voltages and currents in my system. And the easiest way to do this is take this mathematical abstraction called a phasor. And the phasor is a complex number, and it captures the amplitude and the phase of my sine wave. The phasor itself doesn't rotate. It's basically just a fixed vector. And what's important is that this omega here, that I also need to write my complete sine wave, is implicit. It's the same omega as the omega of my source. What are we trying to do here? We're trying to find all the currents and voltages in our system, and they all are going to be sine waves. And the way we're going to find these sine waves is by doing phasor analysis on my circuit. And this is the procedure here. You convert all the sources to phasor notation. So all the sources that are sine waves, you write them as these complex numbers. And then you are going to replace all the circuit elements by their impedances. And these impedances are for a specific value of omega that corresponds to the omega of the source. Then you are going to solve this circuit with all the linear analysis techniques that we know. And we basically are just going to use these analysis techniques on complex numbers now. The key thing is that when I have a system with an R, an L, and C, or any number of those, that these systems are linear. And this phasor analysis only applies to linear systems. That's actually really important. But anything we know about linear systems, all the analysis techniques, we can use. So in the end, you'll find your solution expressed as a phasor. So the last step is to convert it back into the time domain. Let's go through an example here. So I have a sine wave as an input, and I have this circuit, and what I want to know is what is the current here through my inductor as a function of time in steady state, right? So we're not interested in these transition phenomena. We're only looking at steady state, because phasor analysis only tells us something about steady state. So what we are going to do is we're going to represent the source as a phasor and then replace all the elements by their impedances. And you note, for example, that the impedances depend on this value of omega. So now I have a system that I know how to analyze. The only thing is, these are complex numbers. But I can just analyze this with all the techniques that we know, and I can find this complex number IL, this phasor IL. And the last step is convert this complex number back to a time waveform. So basically just use the amplitude and the phase to write this time waveform again for the omega that's the same omega as the source. So that's really the procedure. It's very systematic, and it uses a lot of the principles that we've learned at the beginning of the quarter. What are a few things to watch out for? Well, what if my input was expressed as a sine wave rather than a cosine wave? Well, I can write my sine wave as a cosine. It's actually a cosine just with a phase of minus 90 degrees. So the phasor for a sine wave has this minus j. And so it's actually really important to remember that there is this minus sign here. A lot of students forget that the phase of a sine wave is actually a cosine wave minus 90 degrees. Once you've converted it to the cosine wave like this, it's basically smooth sailing, and you can just express the phasor directly. But that's a good thing to know. The second thing is that you can interpret this phase of the phasor as a time shift. And the time shift is basically minus the phase. And so here I have shown two examples. If the phase is negative, the time shift is positive. So my waveform gets shifted to the right. For a positive phase, my waveform gets shifted to the left. Another interesting thing is that I can look at omega equal to 0. And what is omega equal to 0? That's just DC. And the way to look at this is, well, if I have this time waveform is omega is equal to 0, this is just a constant, right? This is just a constant, basically DC. When omega is equal to 0, my impedances for my inductor and capacitor become short circuits and open circuits. And so when I want to analyze this system in a phasor domain, I'm forgetting here, this is times cosine theta. When I'm analyzing this system, basically my capacitors and inductors become open and short circuits. And this is something we already knew, but this is confirmed now. So basically when I do my phasor analysis, I can just analyze this system with open and short circuits. And then finally, omega is implicit. So when I do my phasor analysis, I'm assuming a specific omega, the omega of the source. Now, what if I have two sources with two different omegas, right? So I have one with omega 1 and one with omega 2 here. Well, this is a linear system, so I can use superposition. I cannot just do phasor analysis directly on this circuit because phasor analysis is for a particular omega. I have two omegas in my system. So I can analyze my system first for omega 1 and then for omega 2. And we can just use superposition as we know. So if I'm only looking at the system for omega 1, I set this source equal to 0. So it becomes a short. If this were a current source, it would become an open. This is something we already know about superposition. And I can also analyze the circuit for just the second source at omega 2. Let's say these are my solutions, then my total solution is just the sum of these two. So I can actually quite easily analyze a circuit if I have sources with different omegas. If I had two sources with the same omega, I can choose. I can either use superposition or I can just analyze it all together because there is just one omega in my system. But if I have two different omegas, I need to use superposition and analyze each source separately. And basically, these are all the things you need to know about phasor analysis.